Significant figures. General rules for significant figures. Significant figures indicate the limits of an instrument. For example, in a typical laboratory balance, the instrument can only measure to the 0.01 of a gram, whereas an analytical balance can measure to 0.0001 of a gram. The scientist using the typical balance cannot report mass values less than 0.01 grams since this is the limit of the instrument. However, the scientist using the analytical balance can report mass to the 0.0001 of a gram. The central purpose in considering significant figures is to determine the number of digits to which an answer must be rounded. Significant figures, also called significant digits, are often abbreviated as sig fig. We will be using simple rounding in this course. You look at the last significant figure from the calculator. If the digit to the right is 5 or greater than the last significant figure, round the last significant figure up 1. Otherwise, leave it alone. All non-zero digits 1 through 9 are significant and should be used to determine the number of digits in rounding. Zeros are the problem in rounding. First rule, zeros between two non-zero digits are significant. So 1005 has 4 significant figures because the 1 and the 5, you have 2 zeros between those two non-zero digits. 407 has 3 because you have 1 zero between the 4 and the 7. Trailing zeros are significant only if it contains a decimal point. 120 has 2 significant figures, whereas 120 followed by a decimal point has 3 significant figures. The decimal point is there to tell you there are 3 significant figures. 1000 has 1 significant figure. 1000 followed by a decimal point has 4 significant figures. Leading zeros are not significant. 0.1. 1 significant figure, the 0 is just there to hold place value. 0.0025, 2 significant figures. The zeros are there just to hold place value. 0.00250 has 3 significant figures because the last 0 is behind a non-zero digit and behind a decimal point. 0.00357 has 3 significant figures. 0.003570 has 4 significant figures. The final 0 is behind the decimal point and behind a non-zero digit. Answers cannot be more accurate than the instrument used. If a scientist, for example, uses a typical laboratory balance, the answer in grams cannot be more accurate than 0.01 grams since that is the limit of the instrument. In multiplication and division, round to the least number of significant figures. As an illustration, a scientist calculates density. The mass is 1.250 grams and the volume is 15.1 milliliters. 1.250 has 4 significant figures. 15.1 has 3 significant figures. The final answer will be rounded to 3 significant figures, the least number of significant figures. Density is mass divided by volume. So 1.250 grams divided by 15.1 milliliters. The calculator gives you 0.082781457 grams per milliliter, which makes no sense because you cannot have that many digits. You have to have just 3 significant figures, the least significant figure in your calculations. So the answer is 0.0828 grams per milliliter. Addition and subtraction round to the least accurate place value. For instance, a scientist measures a series of mineral samples with a typical laboratory balance. The limit of a typical laboratory balance is 0.01 gram. The final answer of a series of addition or subtraction calculations using a traditional balance cannot be more accurate than 0.01 of a gram. For example, the following measurements of a mineral sample were made. Sample 1, 14.30 grams. 4 significant digits. Sample 2, 7.29 grams, 3 significant digits. Sample 3, 2.00 grams, 3 significant digits. This is an addition problem. You add them together, 23.59 grams. The total mass is rounded to the hundredths place, which is the least accurate place value. The correct answer is 23.59 grams. Example 1. Calculate 3.95 times 4.567. The calculator gives you 18.03965. Round to the proper number of significant digits. 3.95 has 3 significant figures. 4.567 has 4 significant figures. Round 18.03965 to 3 significant figures, the least number of significant figures, because this is a multiplication problem. 18.03965. Look at 3, the first digit to the right of the last significant figure. You're having 3 digits. 3 is less than 5, so do not round up. The correct answer would be 18.0. Example 2. Calculate the following and round to the proper number of significant figures. 1.52 is accurate to the hundredths place. 2.4 is accurate to the tenths place. 3.92. We're going to round to the tenths place. Since this is an addition problem, we're rounding to the least accurate place value, which is the tenths place. 3.92, look at the 2, is less than 5, so the correct answer is 3.9. Example 3. Calculate 7.95 divided by 3.580 is equal to 2.220670391 on the calculator, which makes no sense. So we're going to round to the proper number of significant figures. 7.95 has 3 significant figures. 3.580 has 4 significant figures. The final 0 is behind the decimal point and behind a non-zero digit, so it is significant. However, this is a division problem, so we're going to round to the least number of significant figures. 3 is less than 4, so we're going to round to 3. We're going to round 2.220670391 to 3 digits. You look at the 0, which is the first digit to the right of the last significant figure. 0 is less than 5, so do nothing to the last significant figure. The correct answer is 2.22. Calculate and then round to the proper number of significant figures. 9.78 is accurate to the hundredths place. Minus 2.4 is accurate to the tenths place. 7.38 is what your calculator gives you. This is a subtraction problem, so we will round to the least accurate place value. The least accurate place value is the tenths place. So we're going to look at 7.38. The 8, the first digit to the right of the least accurate place value, is greater than 5, so we'll round up. The correct answer is 7.4.